Hello everyone, today we discuss gain controller design using Rootlocus. So here is the example that we are going to solve here. One is we have this block diagram that is given to us, that we have RFS, GC is the controller that we need to design, GPFS is actually the plant dynamics, and we have a unity feedback. Now plant dynamics is 1 divided by S into S plus 1 and S plus 2. So there are three poles actually. This is a third order system and we have to design the gain controller. Now design specification given to us is that our shoot, that is MP less than 0.10, that means that it must be less than 10%. Similarly, we have a settling time, that is TS, and we consider settling time when we reach steady state within 2% of the final value, and in that case it must be less than 2 seconds. Okay, so this 2% means that this is specified that where we are taking the time, okay, when it enter within 2%. For example, if your final value is 1, then within 2% is 0.98 or 1.02. so this specifies this specification. So this is the whole example that we need to design. So if I move to next slide, how we do that. So before designing this, we use the specification. So first specification was that we have MP is equal to 0.10. This means that we have to use a formula to calculate zeta here. So zeta is, if you remember, formula is equal to under root of natural log square of MP divided by pi square plus natural log square of MP. So if I quickly put in the values, so it becomes log square of 0.10 divided by pi square, then plus log square of 0.10. okay, when I solve this, it becomes 0.591. okay, so we calculate the zeta, and next specification is the settling time. So if you remember, it is for 2%, so settling time is 10 seconds. So because why we want zeta and using settling time, we want sigma and omega d. Actually we want to know the dominant poles where our closed loop poles are. So in that case we have a formula says that we have settling time is equal to 4 divided by sigma d, or 4 divided by zeta omega n. okay, so from here we are interested in omega d, so we say that omega d is equal to 4 divided by ts, that is equal to 4 divided by 10, that becomes 0.4. okay, so this is the first part, real part we calculated for the dominant poles where we want to put our closed loop poles. Now the second is omega d. So for omega d we have a formula that is equal to sigma d, then we have to calculate the tan of cos inverse of zeta that we calculate using the overshoot. So when we do that, omega d becomes sigma is 0.4 tan of cos inverse of 0.591 that we calculated few seconds ago. So when we solve this, it becomes 0.55. Now we come up with omega d. We also calculate the sigma d, so we know the dominant pole. So dominant closed loop poles must be somewhere S1, S2 must be equal to minus sigma d plus minus j omega d. So from here this becomes sigma 1 2 is equal to minus 0.4 plus minus 0.55 j. Now we have to pick a design point, so we say that okay, design point, that we call it a P, and we get something that is minus 0.4 and plus 0.55 j. Now we want to use this design point to design our controller. So this is basically the whole idea is based on these specifications, and we calculate it. Now we move to next slide and use this design point to calculate the controller. Now we have to know the characteristic equation. If you remember, we have characteristic equation that we call it as del of s. If you remember, that is equal to 1 plus gc of s gp of s must be equal to 0. From this characteristic equation, we can write that this is 1 divided by k into s plus 1 s plus 2, because g of c is k and plant dynamics must be equal to 0. So from here we can write the k is equal to minus s plus 1 and s plus 2. So this is the formula. Now we have to evaluate k at design point. Now we say that at design point our k s equal to p must be equal to, just plug in the values, that is minus 0.4 plus 0.55 j, that was our design point. Again plug in the values and just do a little mathematics. It become 0.6 plus 0.55 j. Again plug in here and do a little maths. It becomes 1.6 plus 0.55 j. Now this is our point. Now we have to design the controller. So take the magnitude for gain controller. Now we have to calculate the magnitude. So we say that okay, magnitude of k when s equal to p. So take the magnitude of this whole expression. So magnitude, if you remember, we take the under root and take the square, that is 0.4 whole square plus 0.55 square. Similarly take the second one is 0.6 square plus 0.55 square. Then the last one is 1.6 square plus 0.55 square. So when we solve this, I get the value of k is, and that is actually our controller k, that is equal to 0.937. So this is the first step that you have to do, and you do the design. So this is up to design. Now we have to verify this design and then redesign it if we need it. So this is the way you can design your gain controller. Thank you.